Hi there, my name is Charles Sipa. Welcome to another presentation of our e-tutorial series. Our focus today is on method of substitution in evaluating definite integrals. Let's see the first example. Here we are integrating x over x squared plus 1 dx between the interval 0 to 2. I hope you remember that if you've got a function on a system of coordinates like this, and the curve is like that, this is f of x, and then if you're integrating between 2 points A and B, and then the integral of f of x between A and B is a numerical value, let's say a numerical value n, which is numerically equal to the area under the curve of f of x between the points A and B, then this you can put it as a numerical value n squared. How we do that? We normally search for the function f of x, capital letter of x, such that when we differentiate this function, we get f of x. So once we've got hold of that function, this integral equals to capital letter of f of x evaluated from A to B, then we evaluate this as f of b minus f of a. In other words, the value of this function at the upper limit minus the value of the same function at the lower limit, and this is the value which we equate here to this capital N as the numerical value, and this value is numerically equal to the area under the curve there. Then you can say this unit squared, depending on what type of units we're using on our x and y axis there. Okay, so now what we need to do now, we need to do this similar kind of work here, but in this case we need to use the method of substitution. So let's say equals, so let's let our u be equals to x squared plus 1. So which means du dx is equals to 2x, which is equivalent to saying du is equals to 2x dx. But you note that in the numerator here, we've got x dx, then we have to divide both sides by 2 to get du over 2 is equals to x dx. Now we've got an expression with which to substitute the numerator. So what we're going to do here, we'll write the integral here as 1 over u du over 2. Then immediately the question which we need to write here, which we need to ask ourselves, after this substitution, what happens to the limits of integration? What actually happens is we've got to take our u and evaluate it at the upper limit here. Now to take u evaluated 2, and at lower limit we also take u and evaluate it at the lower limit like that. So evaluating that u, we would get u at 0, which is going to be substituting here 0 squared plus 1, you get 1, and then we get you get u at 2, which is equals to 2 squared plus 1, which is equals to 5. So which means this integral now is going to continue as a definite integral from 1 to 5. We can now filter out this half here since it's a constant, and now on the integral side we've got du over u, which is a very familiar integral we've seen before. The derivative we've got here is the derivative of the ln type of function. So we're going to have this equals to half ln of u evaluated from 1 to 5. So now our final answer here would be half multiplied by ln of 5 minus ln of 1. But we all know that ln of 1 is equal to 0, so it will be ln of 5 minus 0. Then we get this as ln of 5 over 2, which you can also write equivalently as you can see, using rules of exponents, this would be half ln of 5, which you can write as ln of 5 to the exponent half, which is the same as ln of the square root of 5. So if you want, you can use your calculator to get that value in decimal place, but you can leave it as this, is not a problem. Then if you want to indicate that, you can just write that as unit squares, just to say that this value is equal to numerical value of the area underneath the curve of this function. So that's that for the first example. Let's turn to the next example, which is as follows. It's similar, not really similar to the problem, but now here what we have got here, we've got square root of x squared plus 4 times x dx integrated. So using the method of substitution, our advice is to let your u be equals to x squared plus 4. Then our du dx is going to be equals to 2x, which is equivalent to saying du is equals to 2x dx. We note again that in this expression we don't have any like 2x dx, but we've got x dx, like x here dx. So then we don't need this 2 here, divided by 2 both sides. We get du over 2 is equals to x dx. So substituting here, we get that as square root of u du over 2. Again, what's going to happen here is that the limits are going to change. The lower limit is going to be u at 0, and the upper limit is going to be u at 2. Then calculating u at 0, we notice that we get 4, and the u at 2 we get 2 squared plus 4, which is actually equals to 8. So now we're integrating now this new function from 4 to 8, filtering half outside, you get half there, and here we've got u to the power half dx. So this half, like we can see, half is not equals to minus 1. So we can continue with our power rule here, which we can write as follows: half u to the power half plus 1 over half plus 1, evaluated from 4 to 8. Then simplifying here, in the denominator we've got 3 halves, and then inverting and multiplying, there we're going to have 1 over 3, and then in this side we've got u to the power 3 halves, evaluated from 4 to 8. So what you're going to have here is fraction, just put it in numerator 3, then we've got 8 to the power 3 over 2 minus 4 to the power 3 over 2. I hope you remember that if you got a rational exponent like this, the denominator, say, you can say square root of 8 to the power 3, and here we've got square root of 4 to the power 3. So we're going to write this as fraction of that. Then we've got square root of 8 to the power 3 minus square root of 4 to the power 3. I hope you can use your calculator to simplify that, and we've got that as a value. You can say unit squared, just to emphasize on the fact that this kind of integral value is equal to the numerical value is equal to the area between the curve of this function and the horizontal axis. Now next is our last example. Most important here, before we talk about the last example, I would like you to note how you change the limits of integration when you use this method of substitution. Otherwise, if you don't change the limits of integration, after integration you go to do backwards substitution and then evaluate the integral again in terms of x. But I think to be just to work one way, you can just change your variable u for that and immediately change your limits and then continue integrating up to the end. Now our last example is as follows. We've got an integral of cosine of x squared over 2. So what we need to do here, we can let our u to be equal to x over 2, then our du dx is equal to half, and then we've got du equals to dx over 2. Again, here we have to simplify because we don't have dx over 2 there. We multiply both sides by 2. We're going to have 2 du equals to dx. So what we're going to have here now is to integrate this as cos of u. Let's write it cos of u times 2 du, write it du, and write 2 outside integral sign. So again here what we're going to have, lower limit is going to be cosine evaluated, not this function evaluated u, not cosine but u. The limits are going to be u evaluated at minus pi over 2 to u evaluated at pi over 2. So taking that, you're going to say u at pi over 2 is going to be equal to pi over 4. And on the other hand, u at minus pi over 2, we're going to have minus pi over 4. So this turns out to be equals to 2 integral from minus 1/4 pi to 1/4 pi cosine of u du. But we all know that cosine as a derivative is a derivative of sine. So then we're going to write this as 2 sine of u evaluated from minus 1/4 to 1/4. Now what we're left now is just to evaluate this, which we're going to write here. This says 2 in brackets sine of pi over 4 minus sine of minus pi over 4. Now, using our identity, know that sine of minus x is equal to minus sine of x. So if you take this minus sign here, we're going to have plus. Then at the end of the day, we're going to have 2 sine of 1/4. So this will be equals to 2 times 2 sine of 1/4, and this gives us 4 times, and you know that sine of 1/4, this is a special angle. This will be square root of 2 over 2, where we have square root of 2 over 2. So simplifying this, we put this equals to 2 square root of 2. And again, I'll write here unit square. So I hope we still remember, just reminding you that now this figure here will be actually numerically equal to the area of this graph between minus pi over 2 to pi over 2. As you know, around the origin, cosine would have released a curve like this, which is symmetric. So this will be, let's say, minus half pi to half pi. So the area roughly we're talking about this area between the horizontal axis x and the curve of the function, in this case f of x, equals to cos x over 2. Okay, up to there, I hope you have grasped the approach which you're supposed to follow in evaluating definite integrals using the methods of substitution. Good luck with your practice. Otherwise, for now, I would like to say thank you for listening.